All right. It's Friday again. Hope everyone had a good week. As usual, this is my office hours. I'm only going to be able to run 30 minutes again today. So if you have any questions or you're stopping by and you have any questions, just let me know. What I thought I would do was solve a few problems while, if no one has any questions, I was just pulling up random questions a bit just to have something to work on and some interesting problems. I have various people who ask me questions randomly sometimes. I'm going to get rid of that. We'll leave that question on the board. But I had someone asking me, we'll get back to this question, but one question that someone was asking me about was they had a polar curve, and this isn't super important right now. It was the square root of the absolute value of sine theta. And only if you're taking BC calculus, or at least you're in second semester calculus, will you do much polar curves. But yeah, a question like this, and the question was sort of like, how do you go about calculating the integral of the area? The area, by the way, is the integral. We're going to do, in this case, we're going to just do the whole area. Oops, not 1 over 2 pi. It's 1/2 integral 0 to 2 pi r squared d theta. And so this is 1/2 integral 0 to 2 pi. When you square this, it just becomes absolute value of sine theta d theta. Oh, and my mistake. It was actually n theta. So where n is an integer. Okay. Now, you might ask, okay, how are we going to approach, something like this? The first thing is to probably get a good idea of what the sketch of sine n theta looks like. And what it means is, like, because it's n, it's going to repeat. If I didn't have the absolute values, and I just wanted to plot sine of n theta as an example, it would look like this, and it would repeat n times, where there's n of these by the time you get to 2 pi. Okay, it's like n repeated periods in an area of 2 pi, in a window of 2 pi. But because it's absolute value, it's really going to look more like this instead. So the real question is what is this total area? Right? That's kind of the big idea. What you can say is, like, each of these humps is the same thing. You just have to decide. So there's n of them. So I can make this n times the integral from this point to this point of absolute value of sine theta d theta, like that. And this first point is, well, this thing repeats every 2 pi. So the way to figure out is, like, what all these points are is I need to know when sine n theta is equal to 0. That's when n theta is some multiple of pi times k. Right? So theta is equal to pi k over n. Now n's like a parameter. It's the coefficient in front of here. But when k equals 0, for example, this is theta equals 0. And when k equals 1, it's theta equals pi over n. So this point here is pi over n. It's the first time past 0, like 0 and pi over n is when this function hits 0. So pi over n. Now, because during this interval, sine theta is always positive, I can take away the absolute value signs. Oops, n theta. Sine n theta d theta. And integral of sine is negative cosine over n. And I still got the 1/2 n here. And I'm plugging this from 0 to pi over n. So this n is going to cancel with that one. It's going to be negative 1/2 cosine of n theta times pi. That's cosine of pi minus cosine of 0. That's this is negative 1 and this is 1, so it's negative 1/2 times negative 2, which is positive 1. So the area under all of this turns out to be 1. I don't know, kind of an interesting problem or approach, but it takes you into an interesting way. How do I deal with absolute values? The way you deal with absolute values is I have to restrict whatever calculation I'm doing. It's not even just integrals, just whatever calculation I'm doing, I have to restrict myself to when the function is always positive or always negative. That's the key idea that you want to do. Yeah. So, yeah. Anyway, I thought it was an interesting problem, having to deal with the absolute values. Incidentally, this has a cool shape. You know, it's kind of like this weird petal. It's kind of like, looks like a flower if you were to graph it. Yep. So I also have a related rates question in here. Sometimes I'll do a mix of physics questions. Maybe I'll do some calculus questions. Kind of whatever's interesting. It could be algebra and pre-calculus. It could be anything, really. As long as I can answer it, I will try to answer it. So. Let me see this question. This question was from, let me get a cleaner version of this question too. It's a little blurry. Fix that. You guys can kind of see how my tutoring sessions typically go. If I do have a tutoring session with the student, it looks a little bit like this. But yeah, so I have a kite that's 100 feet above the ground, moves horizontally at a speed 8 feet per second. At what rate is the angle between the string and the horizontal decreasing? So, let's draw a picture. There's already too many words. I always have to process it kind of slowly, like in terms of drawing a picture. So I have a kite. Look at my awesome kite. Actually, let's make it. I always joke with my students that, you know, one of the things you have to learn when you're doing, whenever you're dealing with physics or calculus or any kind of math or science problem, is you have to be good at drawing really bad pictures, because a picture is so important to understand a problem, and you can spend your time drawing good pictures. Don't get me wrong, good pictures are even better, but you get good at you do enough practice, you get good at drawing bad pictures too. Okay, so it's 100 feet above the ground, moves horizontally at a speed of 8 feet per second. So that's how I like to write it visually for me, as long as I understand what's happening. At what rate is the angle between the string and the horizontal decreasing? So it's the string and when the string has been let out. So it's like kind of like over here, like this is the string and this is the angle, and as it travels this way, the angle is going to decrease, right, over different as it moves along here. Okay. So what they want you to know. So let's this is a related rate question. We have to define this in terms of rate. This is 8 feet per second. Well, I need to assign a letter. So let's say this is x. X is this distance right here. Call that x. So this is really saying dx dt is equal to 8. And they want to know what d theta dt is. Okay. Now the key part of a related rate question is I need to be able to relate theta and t somehow. Theta and x somehow. I need a relationship. Then I can do that. That's always the first step on the setup. Is I need a relationship between theta and x. So between theta and x, because I have a rate dx dt, and I'm trying to figure out another rate d theta dt. So I need to know a relationship between these two. So you think about it long enough, from this picture, I know that tangent of theta is opposite over adjacent. So then I can do take the derivative of both sides of the equation with respect to time. Derivative of tangent is secant squared theta. Then by chain rule, I'm going to multiply by the derivative of the inside times d theta dt. Is equal to derivative 1 over x is negative 1 over x squared. But by chain rule, because this is not t, I got to multiply by the derivative of x, which is dx dt. Okay. So now I could solve for d theta dt. I need to know x. Well, when 200 feet of string has been let out. Oh. Okay, so you know that this is 200. That's what they're saying at this moment. At a specific moment in time, this is 200. That's not x, right? 200 feet of string is this length because this is the string running to the ground here, right? So what is x equal to at this moment? Well, Pythagorean theorem says it's 200 squared minus 100 squared. I can factor out a 100. Yeah, 100. That's going to be a factor of 100 squared. It's going to be a 4 minus 1. So this is going to be 10 root 3. I think that makes sense because because this is if this is 100, this is 200, then this is a 30, 60, 90 triangle, right? Sorry, it should have been 100 root 3. And then that makes this 30 degrees, by the way. So I know my angle now. So I know my angle. My x is this. My angle is 30 degrees. And then I know secant squared, that's 1 over cosine squared of 30 degrees times d theta dt is equal to negative 100 over 100 root 3 squared times dx dt, which is 8. Cosine squared of 30, let's see, cosine of 30 is root 3 over 2. So this is, so I'm going to multiply by cosine squared theta 30 degrees over here to get rid of it on this side. But then that is root 3 over 2 quantity squared, which is 3/4. So then this whole thing is going to end up being negative 100 over 100 squared times 3 times 8 times 3/4. 3's will cancel there. One of these 100s will cancel there. That will cancel be 2. That will be negative 2 over 100, which is negative 1 over 50. And then this unit is radians per second, or radians per whatever unit they are. Yeah, radians. Because the angles are always radians. When we're doing these derivative rules, that's assuming radians. So that is only true for radians. So that was that was a pretty straightforward question. A little tricky to just make sure you had it all set up right, but otherwise it was generally a pretty straightforward question. Let me see if there's any other interesting. Let's look at some physics problems. Now this is from let's see, an old physics honor 7A question. So when I say honor 7A, this is from Berkeley, the physics class I took, H7A. Which is physics for physics majors. It was actually pretty hard. It was really interesting, and I did a video earlier about one of my homework problems that I thought was like really instructive and what I learned a lot about physics. Let's see if I can still do these. These are supposed to be hard problems. When a baseball or softball batter hits the ball, the force on the batter's hands depends on where along the bat the ball struck. The minimum force occurs in one location called the sweet spot. Consider the approximation where the bat is rotating around one fixed point at the very end of the bat, where the batter is holding the bat. Okay. Show that there's a distance ls from the pivot point, the batter's hands, to the location where the ball hits, such that the force perpendicular to the bat along the axis of the batter's hands is 0. You can approximate the bat as a rod of length lb. If you require moment of inertia, please calculate it from scratch. Okay. Let's see. The minimum force. So what we don't know is the location along where the ball is being hit. Okay, this is a torque circular motion question here. So there's a sweet spot here where there's a force being applied here. We need to find this ls to a location that the force perpendicular to the bat's long axis at the batter's hands is 0. They want to show that the force here is only 0. One fixed point at the very end of the bat where the batter is holding the ball. It's an interesting question. So there's a force on the bat. So if I were to draw a free body diagram, there's clearly a force here. When the ball hits the bat, there's a force there. So they're saying that the change, it's moving with an angular momentum. Let's see. It is a collision, so you could talk about conservation of angular momentum. I don't know if that would help you too much. That might help you with the net torque. You'd have to know about how it moved, so maybe it's not super necessary. So suppose, let's see, let's give this a shot. So there's a collision. I feel like I would need to know how the object changes. Its angular acceleration, because really this is the only force acting on the object. Well, I mean, there's the force from the hands, and what they want you to try to show is that there's no perpendicular force here. So this force is gonna cause a torque. It's gonna cause a torque on this bat. So let's assume that this is some ball of mass mv that's heading towards here, right? Has a mass and has a velocity. And then after the collision, the ball bounces off and has mass and times some other velocity. We'll call it Vf. So we have to calculate the change in angular momentum before and after in this system, and this thing is moving at some angular velocity omega. Okay, let's just establish some of these parameters here. So the angular momentum before is we have to establish, since this is a point of reference, this is going to be positive torque, and this one is going to be, sorry, this is going to be positive angular acceleration, and that one's going to be negative angular. So we'd say L is equal to I omega minus M rotational inertia of this thing minus LB, no, LS, this is LS. Man, I'm really bad at rotational inertia, right? It's mr squared is the basic idea for a fixed point mass. So it's M LS squared times the angular velocity, which is V naught over LS. So MLS V naught. Yeah, that's it. That's the angular momentum of that thing. Okay, and so afterwards has a new angular velocity, I omega F minus, so plus M LS VF. And those have to be equal to each other. So the I is equal to, yeah, so those are equal to each other. So because there's no outside torque on the system, I mean, if we're assuming that, if we're assuming there's no force at that point, then there's no well, actually, it doesn't matter. It's at the point of rotation. So there's no outside torque on the system. So angular momentum is conserved. I'm going to have to go here in a second. Okay. And omega F as it relates to this point, it's just the velocity of the bat. Okay, that's fine. That's one relationship we can have. So, conservation of angular momentum. Now, is there a point that you could solve for that? You would have to know a lot of things about other things to sort of reason that out. I don't know. I have to think about that one. That's a hard question. Apparently, I'm not up for, or I haven't, had my brain working on H7 7, 8 questions. Probably requires more calculus than I have available at this moment. Anyway, I'll be doing office hours pretty regularly on Fridays, so if you have any questions, just come by. Otherwise, I will talk to you guys next time.